So we saw how in linear algebra, similar matrices do the same thing with respect to a different basis of the vector space. In other words, we can group together similar matrices, and that's a good thing to do because they have a lot of the same properties. Having all the same eigenvalues, for instance, is a very strong notion of two matrices doing the same thing, being very similar one to another. So we want to take that notion and make it fit into our more abstract context of group theory. So let's take a look at what are conjugacy classes in a group, along with some examples from the groups that we know and love so well. Let's get going. So what are conjugacy classes? Well, we're going to define them in the same way that we define two matrices to be similar. So two elements of a group are conjugate if there exists another element, A, such that H is equal to A inverse times GA. So what properties in a group do conjugate elements share, the same way that similar matrices shared properties within linear algebra in groups of matrices? So first of all, two elements that are conjugate in a group are going to have the same order. Why is that? Well, let's suppose that our element G has order K. So G to the K is equal to the identity. Then what order does H have? Well, if we take H and raise it to the K power, that's A inverse GA raised to the K power. Now, being very careful to avoid writing things in the wrong order, what is A inverse GA to the K power? It's A inverse GA written K times. But of course, when you write that K times, what happens is, according to the associative property that defines a group, we can take the A's and the A inverses that are adjacent and group them together. They cancel each other out, become identities. And then look at what we have. We have a single A inverse at the beginning, and a single A at the end are the only ones that survive. And in the middle, we have K powers of G. But by definition, by our assumption here, the order of the element G was K. Therefore, that element in the middle is the identity. Therefore, H to the K power is also the identity. So if G and H are conjugate, and G is order K, then H also is order K. Also, conjugate elements in a group happen to bring each other along to normal subgroups all the time. They're inseparable in that sense, that any element G that belongs to a normal subgroup, any element that's conjugate to G will also belong to that same normal subgroup. Why is that? Well, let's suppose we have a normal subgroup N inside the group G, and let's suppose that little g belongs to N. Then what about H? Well, if I multiply on the right by A and on the left by A inverse in this expression, then I find out that H, which is what I get on the left-hand side, belongs to the purportedly coset A inverse NA. But because N is a normal subgroup by assumption, A inverse NA, for an element A in the group G, is equal to N itself. Therefore, reading from the far left to the far right of this expression, indeed H belongs to N. So conjugate elements belong to normal subgroups together. That's a very important property for us. Conversely, every normal subgroup of a group is made up of a union of the conjugacy classes of that group. And again, this is more or less by definition of what it means to be a normal subgroup. If I have an element G that belongs to N, then we have to conclude that anything that's conjugate to G also belongs to N. Therefore, the entire conjugacy class, so a conjugacy class is the set of all elements in the group that are conjugate to G, then every element in that conjugacy class will also belong to N. So N is made up of a union of conjugacy classes in the group G. So this seems to forge a very strong link between conjugacy classes of within a group and the normal subgroups of that group. But be very careful, because the converse is not necessarily true. If I just stick together a bunch of conjugacy classes, I don't necessarily get a normal subgroup inside my group, for a variety of reasons, one of which is that conjugacy classes need not be closed under the group operation. In fact, in general, they're not going to be closed under the group operation. Let's look at this quick example. In the symmetric group on four symbols, we have the identity element, which is in its own conjugacy class. That's always the case, by the way. The identity always has no friends in its conjugacy class. And then the conjugacy class of the three-cycle 1, 2, 3 has these 8 different elements in it. Recall that in the symmetric group, the cycle type completely determines the conjugacy class. So what happens if I take these two conjugacy classes and I stick them together? I take their union. It turns out that not only is that union not a normal subgroup, it's not even a subgroup of S4 at all, for a variety of reasons, one of which is if we count the number of elements in this union, there are 9 of them, while the order of S4, 4 factorial, is 24. And according to Lagrange's theorem, the order of a subgroup has to be a factor of the order of the group, but 9 is not a factor of 24, so this definitely is not going to be a subgroup in S4. Also notice that it's not closed under the group operation in S4. If I take these two 3 cycles, 1, 2, 4, and 1, 3, 4, and I compose them together, I end up getting something that's not a 3 cycle, and it's not the identity. Therefore, it doesn't belong to this union of conjugacy classes. So every normal subgroup is a union of conjugacy classes, but not every union of conjugacy classes is a normal subgroup. Let's look at some more examples. How about D4, the dihedral group of the square? Here it's 8 elements, once again. Well, to figure out what its conjugacy classes are, let's first talk about orders. Remember, because conjugate elements always have the same order. So if I list the order of these 8 elements, that gives me at least an initial partition of this group. So all those elements that are order 4 and those elements of order 2 cannot be conjugate one to another. So right away I can divide this into kind of 3 subsets. And we can start looking at whether or not each of those subsets might divide even further into conjugacy classes. So in other words, I know that all 3 of the elements are r squared and r cubed, or order 4, but does that mean that they're all conjugate one to another? Let's pick a couple of elements like r and r cubed. If r and r cubed are conjugate, then that must mean that one of them is equal to a inverse times the other times a, for some element a in the group. Another way to write that is to rearrange it to say that multiplying r on the right by some element is the same as multiplying r to the third on the left by that same element. Can we make this equation work out? And according to the arithmetic in the dihedral group, we can, just by filling in that blank with t, because rt and tr cubed are indeed the same thing in D4. So r and r cubed are definitely conjugate, so they belong to the same conjugacy class. What about r squared? Is r squared conjugate to r? Well, here we have to try a bunch of different possibilities. If we try t, it doesn't work. If we try tr, it ends up not working. If we try tr cubed, it also doesn't work. So try as we might, r and r squared are not conjugate. Therefore, r and r cubed form a conjugacy class, but r squared is in a class all by itself. Now let's take a look at the elements of order 2, starting with t. Let's take the normal subgroup tack for a second. Remember that conjugate elements belong to normal subgroups together. So if I have a normal subgroup in D4, and T happens to belong to it, then what else must also belong to that normal subgroup? So here's a normal subgroup inside of D4. It's the subgroup with generators r squared and t, so it contains these 4 elements, e, r squared, t, and tr squared. Why is this a normal subgroup? A couple reasons. First of all, it's the kernel of a homomorphism out of D4, namely the homomorphism that sends r to 1 and t to 0 in Z mod 2. And that homomorphism looks like this. You can check that's a homomorphism and that h is exactly the kernel of that homomorphism. The other, maybe quicker reason is what is the index of h? In D4, it's 2. And we know every index 2 subgroup is normal. So this is definitely a normal subgroup. Now we know already that e and r squared belong to conjugacy classes by themselves, but what about t and tr squared? Do they belong to the same conjugacy class, or do they each belong to their own conjugacy class? And here's an observation that'll make that a little simpler to think about. Observe that if an element in the group belongs to its own conjugacy class, and if that's the only thing that belongs to its conjugacy class, so the elements that are lonely in their own conjugacy class, that only happens when the element G commutes with everything in the group. In other words, when the element belongs to the center of the group. Why is this? Well, if G commutes with everything, then A inverse GA will always be equal to G. And going the other direction, if there's something in the conjugacy class besides G, then that must mean that that's an element that G doesn't commute with. B inverse GB will not be equal to G. So then the only question is there something with which T does not commute? Well, sure. T does not commute with R, because TR is not the same as RT in this group. Therefore, T cannot be by itself in its conjugacy class, and therefore, since T and TR squared both belong to this normal subgroup, T and TR squared must be a conjugacy class. And likewise for TR and TR cubed, again, because TR doesn't commute with everything in this group, namely because it doesn't commute with T. Check TRT is R cubed, while T times TR is R. So since TR doesn't commute with something, that must mean that it's not in its own conjugacy class by itself. Therefore, it is in the conjugacy class with TR cubed. And so here are the conjugacy classes of D4, 5 of them in total. Next, let's look at the example of S4. This one turns out to be quicker because we know in S4 that conjugacy is just a relabeling of the symbols that we're permuting. So if we first look at what the orders are in this group, we can label the orders of every element. And that gives us an initial division into possibly conjugacy classes, but there's more to it than that, because cycle type in S4 completely determines conjugacy class. Therefore, being order 2 isn't enough to group us into conjugacy classes, because those 2 cycles, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, and the 2 plus 2 cycles are not conjugate one to another because they have different cycle type. Again, the reason for that is that in the symmetric group, conjugacy amounts to nothing more than a simple relabeling of the symbols that we're permuting. So cycle type and conjugacy class are one and the same thing. Let's take an even deeper look at that for a second. That we have 5 conjugacy classes in S4. Let's go a little bit deeper here. So cycle type determines and is determined by conjugacy class. So how many conjugacy classes are there in general in Sn, and how big are they? Well, since cycle type determines and is determined by conjugacy class, the number of conjugacy classes is the same as the number of cycle types. And for example, in S4, the cycle types that were possible were 1 plus 1 plus 1 plus 1, 2 plus 1 plus 1, 3 plus 1, 2 plus 2, and 4. So there are 5 possible different cycle types in S4. Those of them at the bottom here, the 2 plus 2s and the 4s, are called derangements, because every symbol in one of those permutations is moving. None of them are staying in place. So there's 5 different cycle types here, because there are 5 different ways to partition the number 4 into a sum of non-negative integers. Partitions are a big deal in combinatorics. Counting the number of partitions is something that's not easy to do in general. It's done by something called a partition function. So the question of how many cycle types there are is really a combinatorics question, which doesn't really have a very clean and quick and easy answer. But if we could answer it, then we would know for sure how many conjugacy classes there are in the symmetric group Sn. Here's actually a little convenient shorthand for keeping track of partitions, and it's something that if you take a deeper study into representation theory, it turns out that this way of counting conjugacy classes in Sn actually has a lot of additional applications that we can do with it. So let's look at S5 for a second. It turns out there are 7 different ways of partitioning the number 5 into a sum of non-negative integers, and here they all are. And a convenient way of visualizing each one of these is done by something called Young diagrams. Young diagrams are diagrams with squares in them, arranged in a particular way, that helps us to visualize these partitions. So if I take, for instance, the partition 1 plus 1 plus 1 plus 1 plus 1, that corresponds to a Young diagram that has the 5 rectangles, or 5 squares, I guess, arranged in a single row. If I take that diagram and I turn it 90 degrees, I get a partition that has all 5 sort of stacked on top of one another, and that's going to correspond to the partition that's just the single number 5. So in S5, these would be the 5 cycles. The rest of the Young diagrams can be had by using multiple rows or multiple columns. So here I have a row of 4, and then underneath it a row of 1, corresponding to the partition 2, 1, 1, 1. Turn that on its side, and I get 4 plus 1. And then I have here an arrangement of 3 plus 2 and 2 plus 3, so 2 plus 2 plus 1 and 3 plus 2. And then I have one diagram which is the same if I turn it on its side as itself. That's this one, and looks like 3, 1, 1. So Young diagrams begin to look like Tetris pieces after a while. And then each one of these different Young diagrams determines a conjugacy class in S5, which we can use combinatorics then to count how many elements are in each one. For instance, this diagram down here at the lower right, which is made up of the 3 cycles, we can count by counting the number of possible choices of 3 elements out of the 5 to cycle. There's 5, choose 3 of those choices. And then multiply that by the number of cyclic orderings of 3 symbols, which is 3 minus 1 factorial. So there are 10 3 cycles inside of S5. And similar combinatorial arguments can count the number of elements in each of these other conjugacy classes as well. So you can see that there's no quick answer here. But at least if we know how to partition n, then we know how many different cycle types, and hence how many different conjugacy classes there are inside of the symmetric group Sn. And then we can use some rather intricate combinatorics to count how many elements are in each one of those conjugacy classes.